Test. Test. No, still not working. Is there a button on this?
Perhaps.
No, it's just feeling it.
What's the buddy's name?
I don't know.
What's
Test.
Hear
Test.
it?
Oh,
There you go.
you can hear it? Oh, okay, all right. Is it got the 5 second delay in case I swear?
No,
Because that's a really good idea, right?
don't do it.
Come on now. All right. So starting off day 2 of the presentations here now is Dylan Elliott of Marine Engineering Systems 3rd year, and Dylan's going to be talking about exhaust boilers. So Dylan, take it away.
I don't think microphone's on.
It's on, but it's not on this.
It's not on in here.
You know, the one through the picture. I'll need to speak.
It's not online. It's not here. Sort of speak.
No, speakers unmuted.
Yeah, can you hit that?
Under the audio settings, you'll see all the different ones on you.
Oh, that's mute. That's not muted.
That's not mute there.
Yeah, it's not muted at the moment. Hello? Yeah, no, okay.
It's right over there. Test.
Please stop this podium.
Test. No, try that one.
This is selected.
Test. Test. No. Test. There we go.
Wow.
Wow, that was loud.
Hello? Awesome. And
Okay. That counts for my time, right? Ah. Well, like John said, my name is Dylan Elliott. I am a marine engineering system design, and my presentation is on exhaust boilers. So to start off, I actually want to talk about this picture a little bit. This picture doesn't actually show exhaust boilers, but the reason I put this in is it shows a steamship, and I wanted to show the history and importance of boilers used to have in the marine industry. So first off, what's the purpose of exhaust boilers? So the main purpose is to generate steam. Now, this steam can be used for like preheating fuel, produce drinking water, heat water, or heat living areas. So to understand exhaust boilers, you first need to understand what boilers are and how they operate. So the main thing is that the fuel goes in, and as you can see in the picture, that's kind of the fire. So the fuel would go in, it would burn, it produce heat, and then this heat would transfer to the water going through these tubes, as you might see where the red arrows are going through those tubes there. And because, hot and water, that creates steam, and then the steam would come out and go wherever it needs to go and do what it needs to do. So boilers operate using mainly 3 types of fuel. These are coal, oil, and gas. But the problem with these fuels is that they're very carbon intensive, and they cost money too. So the main purpose of exhaust boilers is take away these fuels so you save money, and so that you also save the environment. So this exhaust boilers operate in much the same way as regular boilers. It's just the only fact that they don't use fuel. They use exhaust gases from the main engine or genset. Now, usually what they do is the exhaust gases will come up through the exhaust boiler, and it will heat these coils, like same thing as a boiler. Water is going through these coils, and then that will be transferred and then turn into steam, and then it will go off and do what it needs to do. So one of the early marine boilers that was used was this boiler on the left here. Now, it's not very big, so it was probably just used for heating on like wooden ships. This is before they got invented like the big steam boilers for those metal ships, you see. But this is in 1844, so it's a long time ago now. So this is just a simple calculation we did in class to kind of size our boilers. So that's going to say use the volume of your tanks, times it by a few constants, and then eventually come out with your Q final. And then that will be what you do to size the boilers. So funny story about this. So it's the last day of the first semester of this year. All I got to do now is a simple calculation, right? It's pretty easy. Just get it done. And then I've handed everything and I'm off for Christmas break. So, I'm doing it and I get an answer, and the answer is quite large. So I go to John and he says, well, just try it again, see what happens. So I does it again. I guess the large answer again. So I says, you know what? It must be something right. Maybe I just don't know what I'm doing. So I'm looking around. I can't find any boiler. So I decide, you know what? I'm going to find the biggest boiler they got. So I find the biggest boiler, which is like the size of my main engine. And I think to myself, how many boilers would it take to fit this number? So I does it, and I'm doing it. And I stand up and I look around. Everyone's looking at me, and I say, I need 6,000 boilers on my vessel. And I storm out of class, go right to John's office, and then he helped me out with it. But it's just something simple, like the volume of my tanks was wrong from AutoCAD, and it just ended up the number being really, really large. But other than that, so from that calculation, the boiler I actually chose was this Series 400 with a horsepower 100 from Hearst. And it's just one after, so. So this is a typical layout. I wanted to show this picture because, well, in this picture, they call it waste heat recovery boilers, but I mean, the same thing as the exhaust boilers. They just call it differently. But this picture shows how the exhaust goes from the main engine and gensets through the exhaust piping and then to the exhaust boilers and then out to the atmosphere. So on my vessel, for example, it just goes now from the boilers and gensets straight to the atmosphere without exhaust boilers. But there's one main thing I want you guys to take from this is that there's exhaust boilers, but there's also still an oil-fired boiler in there. So these exhaust boilers aren't exactly meant to just replace your boiler. They're more meant to take the load off and save money and stuff like that. So here's a little table I found online, just trying to explain exhaust boilers. The main thing about it is that the more heat you get from your main engine and gensets, the more you're going to save. So you can see the initial stack gas temperature. It's in Fahrenheit, but it goes 400, 500, 600, and then the numbers get bigger for your recoverable heat. So, but it says on the website, it said that you can save 5 to 10% and it pay for itself in 2 years. Now, that may not sound like 5 to 10%. Why would I install this exhaust boiler? I have to redo a lot of my piping, but it can add up over time. And 2 years isn't too long. I have a lifespan of 30 years for a ship to pay for itself. So here's something we did in class. This is a little Excel spreadsheet on top there with the picture, just showing how much it would cost yearly for a vessel. So it would cost 41 million. And if we apply that 10% that the other slide said, it would cost 37 million. So an amount saved of 4,184,525 yearly. But now, of course, that's using the 10% and under right circumstances. Would you actually save that much? Probably not. But even if it's just half that, you save 2 million a year. And that's not bad. So when would you use exhaust boilers? Well, you'd have to use it with oil-fired boilers, definitely. For example, my ship is an LPG tanker. So I got a very large main engine. My gensets are also very large, and it produces a lot of heat. So you'd use it in conjunction with your oil-fired boiler. You can't use them for smaller vessels. So definitely mid to large range vessels, these exhaust boilers. So this is my main engine I chose. It was the WinGD X72DF. And on the left there, it's a picture of a program the company gave me, just showing the calculations you get from it. But the main thing I chose from it, or got from it, was that the temperatures coming out of the exhaust is 287 degrees Celsius. So right now, my vessel, that just comes out and goes straight to the atmosphere. But that's almost 300 degrees. So you take that and you put that in the exhaust boiler, you can easily make steam out of that. So it'd definitely be used for tankers and stuff like my vessel. So here's something I found online of what it might typically look like. Now, it doesn't look like last picture with the waste heat recovery units, but this is more like realistic, as it actually shows like the structure, and it wouldn't actually just be floating there as a little tiny unit. You can see like the little man down there, and they got like all ladders coming up and all that. But this is the main, like, this is how it usually looks for like bigger ships like mine. So some dangers are with exhaust boilers. The picture of the left is actually showing a fire that was caused, but this happened because they were running their engine too hard. And when you run your engine too hard, the fuel seeps out and gets into the exhaust boiler. And then this builds up, and then as you know, the exhaust boiler is quite hot, it catches fire, and then the fire spreads, and then this happens. So I didn't see anything saying like this is going to happen if you don't run your engine hard. So as long as you don't run your engine excessively hard and at constant rate, this shouldn't be a problem. So the future of exhaust boilers. Well, right now, exhaust boilers can only be used for medium to large size ships. And they have to be used in conjunction with oil-fired boilers. So the future is that they get used for smaller ships, but also the fact that oil-fired boilers are still being used, and these are just for saving purposes right now. So if that can get better, and especially as the energy efficient design index becomes more prevalent, then these things will definitely become, as we're trying to put down our carbon emissions, but also as fuel prices rise, people will start looking more exhaust boilers to save more money and everything. So thank you for listening. Anyone have any questions? Yes, John?
Did you find anything in regards to increase in back pressure? Exhaust system?
No, I didn't go too much in depth with that because I want to give more of a general overview of exhaust boilers and how they operate and how they compare and what you do to save and stuff like that.
You didn't see what the effects of solid.
No. Any more questions? Well, thank you. What?
Okay, guys, up next we have Erin Cook. She's going to be presenting her design project. It's a 50,000 ton weight wood chip bulk carrier.
Thank you, Ian. So this is my third year project. My vessel is named the Humber. So the contents of this presentation is going to include an introduction, the state-of-the-art analysis, line development, general arrangement, powering, electrical design, structural design, tank capacity, capabilities of design, trim and stability, estimated build cost, and my closing comments. So my introduction. The vessel I chose for my project was a dry bulk carrier, specifically a wood chip carrier. I chose this vessel for a few reasons, one being the massive size of some vessels. Dry bulk carriers are among the largest ships in the world and can have lengths up to 300 meters and a capacity of over 300,000 deadweight tons. The cargo variety. These ships transport a wide range of cargo. The diversity of the cargo they carry highlights the essential role they play in the global trade and economic development. Technical challenges. Specifically, for wood chip carriers, a comprehensive understanding of wood chip characteristics is required to safely design one. This vessel is built for Mitsu OSK lines, also known as MOL. The ship will be designed to support Japan's paper industry while also supporting the Canadian forestry industry. State of the art. The state of the art is also referred to as a SOTA. It's a document made to compare ships that are similar in nature to the vessel being built. This document will include general information of the vessel, such as length, deadweight, cargo capacity, engine information, and so on. The SOTA made for my vessel is comprised of wood chip carriers and dry bulk carriers of similar deadweight to my vessel. Some of the problems I had. Unfortunately, for this type of vessel, there wasn't many other wood chip carriers I was able to reference with a similar deadweight. Most of the wood chip carriers I found were sister ships. So half of my SOTA is wood chip carriers and the other half is grain carriers with a similar carrying capacity. I was also not able to find displacements or light ships for my vessels. To find trends within the vessel, these graphs were made to make an estimate of a specific parameter. For this graph, I compared the length overall to deadweight of the vessel from my SOTA. As you can see, my vessel is designed for 50,000 tons, which would end up with a length of just under 200 meters. The final parameters for my vessel. So this method with the graphs was done to find other particulars for the vessel. My final parameters are a displacement of 62,539.1 tons, a length overall of 198.94 meters, a beam of 33 meters, a draft of 11.91 meters, and a depth of 20.61 meters. Line development. The hull form of my vessel. This vessel is a box-shaped vessel with a very wide beam and relatively shallow draft. This shape allows for maximum cargo capacity within the cargo holds while maintaining stability. It also has a nearly flat bottom to facilitate easy and efficient loading and unloading of cargo. The bow features a bulbous bow that helps reduce resistance, minimize slamming in waves, and enhance fuel efficiency. The stern was designed for efficient flow separation to the propeller, and propeller interaction, ensuring a better propulsion performance. Parent lines. Parent lines for my vessel was made in MaxSurf Modeler, where I first made a cylinder shape and used a series of control points to effectively design my length, beam, draft, and depth for my ship. Once this was complete, I added more control points and faired out the vessel to ensure smooth and fair curves throughout the hull. I was also checking to make sure that the displacement of the MaxSurf vessel was also similar to my original displacement. Finally, the lines plan drawing was created by exporting lines I created in MaxSurf. These lines were then put into an AutoCAD file to create the final lines plan drawing. My general arrangement. Profile. This ship has 6 cargo holds, which is typical for wood chip carriers. This vessel also has a lot of ballast tanks because it needs to carry ballast up to 11,000 tons. To reach the ballast capacity needed, hopper tanks were added to help manage my ballast. My main deck and tank top. As you can see, my main deck consists of my cranes, cargo hatches, and mooring equipment. The superstructure is where my provisions are located, along with my crew workspaces and the hospital. The tank top consists of my cargo holds and the location where my engine is. This view also shows my propeller and my bow thruster tunnel. My decks. Located on Deck A, I have a galley, mess, theater, gym, and the emergency genset room. On Deck B, I have crew cabins. On Deck C, I have my higher up cabins, along with the conference room and a computer room. Deck D is where the captain, chief engineer, and chief officer's cabins are. And finally, I have my bridge deck and my compass deck. Powering. The effective power calculation. A series and regression analysis of Holtrop and Menon was done on this vessel to calculate the total resistance. The resistance is needed to calculate the propeller diameter. Once this was determined, the power can be calculated to select the right engine size. Selecting the engine. The total resistance for this vessel was 1,491.55 kilowatts. The propeller diameter needed was 7.18 meters. Using this information, the minimum MCR power was 9,479.5 kilowatts. So the engine selected was a MAN B&W G50ME-C 9.6 low-speed diesel with a capacity of 10,320 kilowatts. Propulsion configuration. This vessel will have a 2-stroke diesel engine and a fixed-pitch propeller, along with the appropriate shaft, bearings, shafting system, rudder, and steering gear. Since this vessel is going to the Vancouver port, where it will have to navigate around some islands to get into port, bow thrusters have been added to aid with maneuverability. Electrical design. Genset powering requirements. For proper efficiency to the gensets need to be running at an 80% capacity. For sailing, the vessel used a power of 2,836 kilowatts. A Wärtsilä 6L32 with a power of 3,480 kilowatts was chosen. For anchoring, a power of 2,529 kilowatts was used, and a Wärtsilä 9L29 with a power of 3,060 kilowatts was chosen. For loading and discharging, the vessel used a power of 2,815 kilowatts, and the same Wärtsilä 6L32 was used as per sailing. For maneuvering, the vessel used a power of 3,410 kilowatts, and a Wärtsilä 6L32 with a power of 4,489 kilowatts was chosen. Finally, my emergency genset used a power of 3,845 kilowatts, so the genset was a Wärtsilä 8L32 with a power of 4,640 kilowatts. My genset locations. For this vessel, the gensets are located on the third engine room platform. I originally had them on center line to the right of the cutout for the engine, but I had to move them because they were too big to fit there with my steering gear and my ballast tanks. My emergency genset is located on Deck A next to the engine casing to allow for proper ventilation and easier access. Structural design. The material used for my ship is a high tensile steel. The Lloyd's Register was used for Classification Society, which will provide classification and certification for the vessel. A longitudinal framing system is used throughout the vessel and a transverse framing system is used on the fore and aft ends of my vessel. The longitudinal framing is used to help distribute the loads along the length of the ship, and the transverse framing system is used on the ends of the hull to maintain shape and strength. Hopper tanks. Within my cargo holds, there are hopper tanks present. These are very important for this type of vessel. These are used to help with discharging cargo. It creates a ramp-like structure where the wood chips cannot get stuck into the corners of the holds. Wood chips have a very low cargo density, which makes my vessel very light and can risk stability of the vessel. This can also affect my propeller immersion angle. As said before, these hopper tanks will be ballasted to help weigh down the vessel and help with these issues. Tank capacity. The main capacities of my vessel are as follows: a freshwater capacity of 48 tons, a gray water capacity of 25.75 tons, a black water capacity of 26.5 tons, a ballast capacity of 16,452 tons, fuel oil capacity of 860.3 tons, a lube oil capacity of 24 tons, a cylinder oil capacity of 38.5 tons. The locations. My freshwater is located on my tank top along with my gray and black water. My many ballast tanks are spread throughout my vessel. Most of my vessel is actually ballast tanks. Capabilities of design. This vessel is designed to maximize cargo capacity while ensuring safe transportation of wood chips. This design includes an optimal configuration of my cargo holds, allowing for efficient loading, stowage, and discharge of wood chips. It's designed to withstand the forces exerted during loading, unloading, and navigation while maintaining stability for a safe operation. This design ensures good maneuverability, allowing for the vessel to navigate safely in confined waters, berth efficiently, and handle different weather conditions. It's also equipped with specialized cargo handling equipment to effectively load and unload the wood chips. Trim and stability. The trim and stability of my vessel was run for each of the following conditions: light ship, primed light ship, port departure, with and without cargo, mid-voyage with and without cargo, and port arrival with and without cargo. The full load of my ship. Port departure with cargo is when the vessel is fully loaded. The vessel has a ballast in the bottom aft tanks and half filled in the fore tank. The worst condition for my vessel was port arrival with no cargo. As you can see, the vessel needed ballast. To ballast 2 cargo holds in order for it to stay upright along with the forward ballast tanks. If these holes were not ballasted, the vessel would have a large trim and heel and would end up heeling over. Estimated build cost. The Carriette method has set up regression equations for estimating labor hours required to build a vessel. Using these equations, different costs in the building of the vessel were calculated. This method was relatively good for my type of vessel, and a reasonable estimate of $75,963,425 was made. Conclusion. If I was able to do another spin around the spiral, I think I would be able to improve my machinery arrangement. I would optimize engine room space by rearranging my engine room equipment and add more in. Maybe even moving my bulkheads for my engine room to make it bigger so I'd be able to fit my gensets on centerline. I would also improve the cargo handling facilities. I would add self-unloading conveyors to help enhance the efficiency of loading and unloading cargo. That's the end of my presentation. Any questions? Yeah.
I think
My vessel is named the Humber because it's actually the nickname of my boyfriend.
Also, go back to the second slide. Would you ever go back to like the second slide for 1 second? I think it was one of the first couple slides anyway. Picture the vessel.
That one?
That one.
Oh, that one?
Okay. Yeah, I thought so. Is that wood chip carrier symbiote? Like, is that an actual wood chip carrier?
Yes. I'm pretty sure it is.
Okay. Notice something on that? That is unique.
It has the wings coming out.
Yeah, that's that. I know we've had some issues with the volume because of the densities of cargo, volume-based, or the density-based design. And just to the side, I saw that. I never captured that in any of the design, Minnesota and such. But that looks like it's there as improving or increasing the volume of the cargo, or having those little. They're not sponsons, but they kind of look like a. I don't know how far that goes outside. I'd be interested to look at that ship with more details. So I know that was one of the challenges for you, was because the densities of the wood chips, wet or dry, really made it was a volume issue more than how they were stating there.
Right. Right.
Can you suggest what did you have for your cargo handling? You suggested that it was specialized. What was the actual cargo handling you had now?
So I have 3 grab cranes on my vessel for unloading. Any more questions? Yeah?
You mentioned the possibility in the future, looking at these on hoppers for conveyor system, self-unloading system. Is that common on wood chip carriers or?
Yeah, so right now, Mole is actually doing a lot of research with it, and they have a couple new vessels coming out that actually have conveyor belts on the vessel to help unload the wood chips. So the grab cranes would actually go down and grab up the cargo, and it would be put on the conveyor to just move it to the dock.
Conveyor would actually be on the deck.
On the deck, yeah.
Oh, okay, so it's not like a typical self-unloader, the conveyors are below the actual.
No. Any other questions? Yeah. Oh, sorry.
One quick question for you. Was there something special about your vessel emergency mode? Like, is there something special about your vessel emergency mode?
The emergency mode?
Yeah.
So for my vessel, do you mean like with like if it wasn't
Well,
fully cargo?
no, just wondering, because it looked a little high. So I was wondering if there's some special thing going on that has to happen for emergency situations.
No, I didn't. Okay.
Just curious.
Okay. Any other questions? Thank you.
Okay, folks, thanks for that. We are going to break now. We're leaving, or breaking a little early, but we'll resume the presentations again at 10:30. Okay? Thank you. The folks up next, we have Amber Tremblett. She's be doing her design project on a boat, tanker, product carrier. I'll let her give you the details.
Thank you for that introduction, and good morning, everyone. I am Amber Tremblett, and today I'll be presenting to you my project vessel, the Irish Princess, a product tanker. A quick overview of everything I'll be covering today. First, an introduction, then the state-of-the-art analysis, the lines plan, the general arrangement, the powering, the electrical, the structure, the capacity plan, the ship's capabilities, stability and trim, the estimated price, and finally, my closing comments. So first, the introduction. Everything started with the mission profile. The mission profile is the starting point for this project and outlines the route forward. This ship is being designed for the Irish tanker fleet and operates worldwide. Many of their current tankers are around 20 years old or more. This ship is being designed as a replacement for this aging fleet. Instead of a regular A to B route, the ship will deliver cargo to 3 different places along its route. When deciding what places to deliver cargo to, there were a few things I had to keep in mind. Do these places already have treaties with other countries for oil products? Or as well, relations between other countries, such as US and Cuba? And do these places have their own refineries? For many of the places I looked into the region the ship is operating in, checked one of these boxes. Overall, the design for the ship was focused mainly on cargo carrying capacity to maximize revenue. This is the route that the ship takes. The ship's home port is right here in the port of Port Everglades in Florida. From here, it leaves and makes its first stop in Cayman Brac in the Cayman Islands. Next, it will head to Lime Tree Bay in the US Virgin Islands. The final stop is Freeport in the Bahamas. And then back to Port Everglades to load up and make the journey again. On to the state-of-the-art analysis, also called a SOTA, is a method consisting of gathering data of similar things to your project to use as a reference and justification for design choices. This data gathering process was our next step in the design process. Using an online database, I gathered information from 50 ships that were product or chemical carriers that ranged in deadweight values from 30,000 to 50,000 tons. This is a big range. This big of a range was used to have a large enough set of data points to notice trends better, as well as be able to use the equations given by the Excel graphs for more accurate points along the trend line. All the information was organized into a huge spreadsheet to use as a reference. A lot of this data was then used to develop a number of graphs to visually see any trends. Using the trend line and adding design lanes, these trends and data relations were used to get an idea of the ship's parameters. So a couple of trends that I found. The first was that a lot of the ship's beams were 32 meters. This is because of the old width of the Panama Canal. The other trend I noticed was that 14.5 knots was the most common speed among all the vessels that I had. Now, some problems that I had. First was that I had little to no information on what type of cargo any of the ships carried, besides being a distinction between the ship being a product carrier or a chemical carrier. I'll touch more on this issue later. The next problem was that the actual displacement values for the ships were rare. I was able to estimate the displacements by using the given deadweight and lightship values. The final problem I had was I never had much data on how many crew members there were, and any that I did weren't enough to notice any trends. So I ended up basing my crew number on how many cabins I could fit in my superstructure. This is one of the graphs I created with my SOTA data. This graph is comparing the length on the waterline to the ship's beam. You may notice this cluster of points right here. And if we check the axes, all these points are around 32 meters, proving of what I just mentioned about the old Panamax size. After gathering the SOTA data, we also used a series of empirical formulas to calculate values. It was using a combination of these two methods that I chose my ship's final parameters, and they are as follows. A deadweight of 46,000 tons, a displacement of 55,222 tons, a length on the waterline of 172.5 meters, a beam of 32 meters, a depth of 18 meters, a draft of 12.2 meters, a block coefficient of 0.8, a surface speed of 14.5 knots, a Froude number of 0.181. Next is the lines plan. A lines plan is a drawing with 3 different views. The profile view showing the buttock lines, the plan view showing the water lines, and the body plan showing the station lines. It is this drawing that shows all of the hull shape. Getting the hull shape right is one of the most first important steps in the design. Here's my profile view of my lines plan. There isn't anything too notable, but I will point out that my hull form does have a bulbous bow. While many ships have a bulb, this type of bow is only beneficial for certain ships. The amount that the ship benefits from is based on the ship's Froude number and its block coefficient. For my ship, adding a bulb would be 0 to 5% efficient to not having one, so I decided to use that bow shape. Bulbs can have different shapes. I chose to use an upside down teardrop shape. This shape is also referred to as a volume type bulb. While I did have the option to use a parent hull, I chose to make my hull from scratch, starting with a simple cylinder and developing it from that. Like many cargo-based designs, my hull has a lot of parallel middle body to maximize cargo space. So creating a balance between maximizing cargo while also having a good transition areas in the forward and aft shoulder. Now for my general arrangement. The general arrangement is one of the most detailed drawings. It consists of a centerline profile and a plan view of every deck. It will show all the different rooms, the machinery, equipment, and furniture. First, here is my centerline profile. A few things to note first. Taking up most room in my hull is my cargo tanks. I have a total of 12 cargo tanks with 6 port and starboard. In the aft is my machinery space, which is where the main engine is located. Then there's the accommodation block that we'll be looking at in just a moment. Starting on the main deck, over here are the various food stores. There's also a wider door frame leading to outside so that pallets are able to be wheeled in. Separate change rooms for the deck crew and engineers. One of the most important places on my ship, the cargo pump room, is located right here, and then the fire control room. Going down to the tank top, once again, there are all 12 of my cargo tanks, and back aft is the main engine. Going up to the lower engine platform, again is my main engine, and here are the 3 main generators. Going up again, there is my upper engine platform. Again, there is the main engine. Ooh. The upper engine platform, we have the fuel, settling, and day tanks, as well as the engine control room. Now into the superstructure. Starting with A deck, we have the cargo control room, the galley, and then the mess and day rooms for the crew and officers. D deck is mostly crew cabins, but it also has the emergency generator room. C deck is all crew cabins. D deck has 4 more crew cabins, most notably the captain's cabin. And finally, this is the wheelhouse. Now for the powering. Through this process, the main engine and the proper propeller was selected. First, a preliminary power was estimated using my SOTA data and formulas. This is another graph I made using my SOTA data. Using my chosen speed of 14.5 knots and the trend line, the preliminary power is estimated around 9,000 kilowatts. However, when the final brake power was actually calculated for my ship, the actual value was closer to this point all the way up here. I do think that this is because of the age of the similar ships I had collected. The total ship resistance had to be known first before calculating any power values. I used the hull trap amendment regression analysis method. This method consists of calculating various different types of resistances that the ship will face. With the ship's total resistance and effective power was calculated using the resistance total multiplied by speed. The effective power is brought forward using various efficiencies to get the brake power. It is the brake power that is used to size the main engine. The chosen main engine is a MAM B&W 7G50 ME-9.6 at 12,040 kilowatts. My propulsion setup is fairly simple. I have a low-speed diesel engine with 1 shaft and a fixed pitch propeller. The propeller is a B465 propeller and has a diameter of 7.3 meters, and was sized using propeller charts and cavitation charts. When sizing the propeller, there were preliminary calculations done to get an idea of the maximum size the propeller can be, and then the stern was designed to accommodate this propeller size and have the appropriate space left for tip clearance. Next is the electrical. With this section, the electrical needs of the ship were assessed to determine the size of the generators required to power the ship. And here's my single line diagram showing my main and emergency bus bars, the connected loads, and the required transformers. The process used to properly size the main and emergency generators is as follows. First, there was a load listing done. This lists all the loads that are on board the ship. Using the ship's operating profile, the loads were broken down into what operating loads they are used in. Each load was assigned a load factor. This factor is based on how frequent the load is used. For the emergency condition, it is sized for the worst case scenario. So all loads in that condition are considered to be constantly running. This made the emergency load 220.7 kilowatts. The largest load from the other operating conditions is used to size the main generators. This value was 1,795.3 kilowatts. When picking out the main generators, it is important to make sure that the generators have a good utilization in all operating loads. It was this that led me to the choice of 2 larger and 1 smaller generator. A previous configuration of 3 larger generators worked good for the largest operating condition that I had. However, I had very poor utilization in my other 2 operating conditions. The smaller generator helps with this problem. The main generators are located on the lower engine platform. The 2 larger generators are 1,110 kilowatts each. A smaller generator is 740 kilowatts. The emergency generator is located up on B deck and has a value of 300 kilowatts. Now for the structure. All the structure is shown in the profile and deck drawings along with various construction sections. Here as you look at the midship section, some structural features I'll point out is the corrugated bulkheads and the bulkhead stools. Both of these features are to help get all the cargo out of the holds by not having anywhere it can get trapped and to help it gather in the center of the tank. This also helps with tank cleaning. All the ship's scantlings were calculated using Lloyd's rules. This stage of the design process had a big impact on my cargo capacity. As with the size of my ship, the hull has to have a double skin, meaning that I have to have space between the outside world and my dangerous cargo. This is done by having a requirement on the minimum height of my tank top and a minimum width of my tanks. The tank top was able to be lifted to the minimum requirement, but the wing tank's inboard bulkhead had to land on a frame space, which meant that the wing tank ended up being wider than the minimum amount. Both of these changes did have an impact on my cargo capacity. The choice of material was Lloyd's grade A steel. For longitudinal strength, the ship was longitudinally framed, and in the fore and aft ends, the deck will continue to be longitudinally framed, but the sides and the bottom will be transversely framed. And as mentioned before, the corrugated bulkheads and stools are good for liquid cargo. Next, let's look at the capacity plan. This drawing shows the locations of all the tanks on the ship. The drawing will also have a table listing of the names of the tanks, their locations, and their capacity. Some of the required capacities, such as the lube oil sump, were given in the project guide, but any that weren't were calculated to determine the minimum required amount. To satisfy the ship's range, the ship has to have enough fuel on board for 3,500 nautical miles. And to satisfy the ship's endurance, there has to be enough fresh water on board for 14 days for 24 people. As well, it's important that there is enough ballast capacity to keep the ship stable when there is little to no cargo on board. So for my calculated values, I required 40.32 tons of fresh water, 490.52 tons of fuel oil, 25.36 tons of lube oil, and the estimated ballast capacity was taken as 40% of the estimated cargo capacity, which was 19,496.2 tons. Now for the actual values, there are 46.88 tons of fresh water, 561.96 tons of fuel oil, 33.77 tons of lube oil, and 18,009.59 tons of ballast. While this is lower than the estimated value, it is a sufficient amount to keep the ship submerged at a good draft. This is a view underneath the main deck, and the most notable tanks are my cargo tanks, the MDO storage, just settling and day tanks, and the wing ballast tanks. Other tanks that aren't shown here are in the double bottom. On to the capabilities. First off, this is one ship going to 3 places instead of 3 different ships going to each place. Every day spent in the Caribbean, which is a really big plus. By having corrugated bulkheads and stools, tank cleaning and cargo removal is much easier. There is enough fuel for a transatlantic range. The ship can also fit through the Panama Canal, so it can be used for various other missions should its mission have to be changed. The ship is able to carry various types of liquid cargo, diversifying its mission even more. And finally, the main engine uses MDO instead of HFO, which, while still producing emissions, is better for the environment than HFO. Next is trim and stability. The regulations used for TP 7301E from Transport Canada. 9 conditions were ran to see the ship's stability in various operating loads. These 9 conditions are light ship, primed light ship, fully loaded port departure. After Cayman Brac, the ship is 2/3 loaded. After Lime Tree Bay, is half loaded / mid voyage. port arrival, loaded port arrival, mid-voyage with no cargo, and finally port departure with no cargo. Any condition that did not pass or did not have sufficient propeller immersion had ballast added until the condition was suitable. This is what the ship looks like in its at port departure with a full load of cargo. There is enough propeller immersion and the ship is trimmed a bit. The best thing about this is the draft, 12.1. And the draft I have been designing for is 12.2, so this is very close. The last topic for today is the estimated cost. Prior to calculating the price, the wage for the machinery, outfit, and steel were calculated and estimated. The carry-it method was then used for determining the various costs. The total of these costs, along with a sufficient margin for shipyard profit, the total estimated bill cost was calculated. Prices of very similar ships were gathered and brought forward to today's market, and this ship was cheaper by roughly 10 million at least. The final cost to build a ship in North America is 84.5 million USD. If the ship was built in Europe or Asia, the cost would be lower due to higher efficiencies and lower wages. And now for my closing comments. With an additional turn of the design spiral, some improvements I'd like to make are a more detailed machinery arrangement, a more accurate steel weight. I'd like to do more digging into finding out exactly what type of cargo my similar ships were carrying. As I noted earlier, I never had any data on exactly what the similar ships carry. And this turned out to be a problem when examining the tank capacities and the stability conditions. Initially in the mission, the ship was to carry gasoline, but the density of gasoline is relatively light. So when I was running my conditions, I discovered that I was not meeting my deadweight requirements. This problem was because of the fuel density. I do think that with another turn, I'd look into carrying a denser cargo or researching how similar product carriers meet their deadweight requirements when carrying lighter cargoes. I'd also like to refine the design for my cargo manifold. And for my overall design, I'd like to possibly investigating extending my ship's length. And that is all for me. Thank you for your time today. And are there any questions?
Safety of occupants having fuels in our gas systems. What do you have for gas systems on ship? How do you manage that?
I do have my inner gas system, and in case things go wrong with that, there is a fire control room to help with the systems for putting that out, should that happen. And there is also the lifeboat station at the back, so then everyone is able to quickly evacuate from the superstructure and get off the ship should everything, be going haywire.
Your gas system is this, like, carrying your gas on board or using exhaust gas?
My plan was to use part of the exhaust gas to create the inert gas on board to continuously be producing that. John?
Maybe this is your presentation in there, you mentioned that one of the what they're doing, redesign was to lengthen the ship.
Yeah.
Any particular reason why you would look at lengthening the ship?
That's mostly to extend my cargo little body, so then I have more room for cargo, so I could possibly meet that deadweight requirement a bit easier. Yes.
Small question.
If I was to extend my beam, I'd also extend my length as well, just to keep that ratio even, because I was very good with my length to beam ratio. Yeah. Anything else?
Yep. Test, test, test. Okay. Hmm?
Oh, I don't know.
What was that for?
Which one? Did you say there was?
No, no, you're good.
Yep. 1 second. Okay, I'm ready.
All right, so save the best for last, right? This is our final presentation for both Narcan Systems. It's Mr. Tony Kirkland, and he's hopefully going to be graduating in a couple of weeks. I have confidence that he will. And his presentation is reducing noise pollution in research vessels. So take it away, Tony.
Thank you. Yeah, so my name is Anthony Kirkland, and I'll be talking about reducing noise pollution on research vessels. The agenda for today, I'm going to talk about silencers and how they're used to reduce noise pollution for engines and gensets. I'm going to talk about resilient mounts and how they're used to reduce vibration noise from equipment, noise canceling insulation and its design considerations, and propeller maintenance problems that can arise and how to reduce it. The scope of this project is to address the 4 potential solutions for reducing noise pollution and relate them to my project vessel, a 63-meter oceanographic research vessel. So this here is my machinery arrangement for the engine room of the research vessel. When designing the machinery arrangement for a smaller vessel, such as this one, it's important to utilize the space available as best as possible. So if you look over here, these are my fuel tanks right here. And so I put my fuel pumps right next to them, as well as the purifiers. If you look right here, this little box here and this little box here, those are my sea chests. So there'll be a cross connect that goes through here. And so any of the pumps that use seawater, I tried to put those as close as I could to the crossover, so that there'd be less piping involved and I'd have more space for other equipment. The main engine I chose for this vessel is a Wärtsilä 8L20 with 1700 kilowatts of power, chosen from a similar ship's analysis. The operation of this vessel will be to leave the St. John's Harbor and head to the Grand Banks for fishing and research. The engine will run at 85% capacity and reach its destination, taking approximately 61 hours. The engine will run at 50% capacity for other means such as fishing and research. The gensets that I chose are 2 4L20 Wärtsilä generators with a power of 740 kilowatts. One will be running 24 hours a day while out at sea, while the other will be kept on standby. This genset will provide power to the electrical loads of the vessel. This is the piping arrangement for my engine room. If you look right here, these connections here and these connections here, those are my cooling systems. And the cooling systems connect to the plate heat exchangers, which provide cooling for the main engine and the two gensets. The hardest part of my design was trying to fit those into my engine room, because with all the other equipment and needing the 4 plate heat exchangers, it was hard to find the best way to fit them in. The way I have it organized is so that there's 1 plate heat exchanger for each genset, and there's 2 plate heat exchangers for the main engine. The ballast system runs right up to here, and that had other different design considerations. So the cooling system here has the pumps, the strainers, they have a starter box connected to them, and they lead into the plate heat exchanger. The small orange lines here that go around the pipes, those are pipe hangers just to help stabilize the piping. The ballast system right here, this is the ballast water treatment system. And as you might note, I have the pipe connections going up vertically instead. I was really running out of space, and it was the best option at the time for fitting the equipment in a reasonable place close to the cross connect, while also trying to utilize the space as best as possible. Reducing noise pollution creates a better living environment for the crew and passengers. It is also important to reduce noise pollution in the water to minimize damage to marine life and not to disrupt the research data. But how much noise is too much? Studies have shown that its general noise levels above 120 decibels can cause temporary or permanent hearing loss to marine life. However, even lower noise levels can disrupt their communication, foraging, and migration patterns. For a research vessel, the goal is to achieve noise levels for below 65 decibels. And it's also known too that for people, anything above 80 decibels for long periods of time can cause temporary to permanent hearing damage. This picture here shows a section view of the exhaust arrangement for my project vessel. The piping here, coming from the main engine and the gensets, goes up through the casing and up to the top, where the exhaust fumes will escape. These cylinders here are my silencers. The smaller one is for the genset, and the larger one behind it is for the main engine. The main engine silencer is a critical cylindrical silencer JB20, right here. And the genset silencer is also a critical cylindrical silencer JB12. If you notice the little speckle background between the lines, that is insulation, and that is used to help dampen noise and also to prevent heat loss. I'll be talking about 3 types of resilient mounts: vibration isolating mounts, vibration isolating hangers, and vibration isolating pads. If you look here, what I chose to show for this section is a vibration isolating hanger. So these right here are mounted to the foundation, and the foundation will hold up either the ductwork or piping to be suspended up in the air. Resilient mounts are placed between the machinery and the deck of the vessel. These mounts reduce the vibrations and transfer them into the structural members of the vessel. So as you can see, the engine here, these would be the resilient mounts, and the vibrations would be reduced going into the structural members and then into the shell of the vessel. The goal is that the vibrations will be reduced in this process, and then when they escape into the water, or into other parts of the vessel outside the machinery space, it'll be at a low enough decibel to not cause any hearing damage or discomfort. If these decibels are too loud, even if it's below what would be damaging to your hearing, it can cause extreme nausea after long periods of time. Vibration isolating mounts are used for switchgears, transformers, boilers, cooling towers, compressors, and other heavy equipment. They are seismically rated, available in a wide range of sizes and configurations. They have multiple attachment options and also have light duty mount options available. Vibration isolating hangers are used to suspend objects such as fans, ductwork, and piping. They reduce the shaking leading to loosening of bolts and screws. They limit the damage to equipment and also reduce efficiency loss. Vibration isolating pads are used for medium and high speed equipment. They are available in different sizes, thicknesses, and material. This threaded top right here is used to minimize slip. They're made from a durable rubber blend and cork material and can be easily cut to be adjusted to different sizes and shapes. Engine room noise dampening insulation. So as you can see, this colored part right here is the insulation. So this insulation is used to dampen the noise coming from the machinery and also to prevent heat loss. It is important to note that when placing the insulation, you have to be aware of the spatial awareness, because especially when you put in some of the larger systems like air ducts and the exhaust, the piping can be quite large, and also the insulation needs to go around it. So you need to account for the size of the piping, the insulation to go around it, and then the insulation to go around here. The insulation I chose was a vinyl foam barrier composite. It is available with or without pressure-sensitive adhesive backing. And this is what would be used to absorb the unwanted noise pollution and also retain heat. In this section, I will be talking about potential damage hazards to propellers and how that can lead to noise pollution. As you can see, this propeller here is pretty tore up. Propeller cavitation is the main source of underwater sound. Cavitation is when water vaporizes or bubbles due to extreme reduction in pressure on the back of the propeller blade. You can see in the rotation of the propeller, this action here can cause bubbles on the backside. The implosion from these bubbles causes pitting on the propeller blades, chipping away at the metal. This in turn can lead to vibration and noise pollution while running and reduces the propeller efficiency. If enough pitting happens to chip away the metal, it can take away the balance of the propeller, causing a large thumping sound. And this thumping sound can cause extreme nausea in some cases. Ways to reduce propeller cavitation. Proper propeller design. The design of the propeller plays a crucial role in minimizing cavitation. The reduction in rotational speed. Lowering the rotational speed of the propeller can help decrease the chances of cavitation. This can be achieved by adjusting the engine RPM or through the use of reduction gearing. Increase the blade thickness. By increasing the blade thickness, the risk of vapor bubbles forming and imploding can be reduced. Adjusting the blade area ratio between the propeller's root and tip can impact cavitation. By modifying the blade area distribution, particularly at the tip, can mitigate cavitation effects. Using advanced materials and coatings. The use of advanced materials and coatings can improve the performance of propellers and minimize cavitation. Composite materials or special coatings can enhance the strength and surface properties of the propeller blades. Hull and propeller fairing. Ensuring a smooth transition between the hull and the propeller can help reduce turbulence and cavitation. Although it is not likely to completely eliminate noise pollution, there are many ways to help reduce it. The methods I discussed, engine and genset silencers, resilient mounts, engine room noise dampening insulation, and propeller maintenance are just 4 of many ways to mitigate this problem. Are there any questions? Yes?
We talked about silencers.
Hmm.
What you do need. Just look at your grades of silencers. Which ones are the best in town?
I mostly looked at the cylindrical silencers because they were the best for what I was looking for. For the type of ship I had, they met the requirements that I needed. There was other cylindrical silencers that would also work, but they were much more cumbersome.
In regards to size,
Yeah, in regards to size.
like hospital grade, you got pretty good, right?
Yeah.
So you look at hospital grade.
They could possibly work as well, but I didn't fully look into those. Yes, Kevin?
You get a chance to look at any of the lower manufacturing techniques of materials that are used in sealers, any advancements in reducing cavitation?
Sorry, could you say that again?
I'm not sure. You get a chance to look at some of the new propeller production techniques and some of the materials that are used to see if that's a way to reduce cavitation.
Yes.
So there is new technology coming out where you can even 3D print propellers, and this effect looks like it can reduce cavitation. It is still in the trial period, so it hasn't been fully tested out, but it is looking promising for a good way to reduce cavitation.
Your vessel, what is your vessel mission again? You're just a research or seismic research?
This research. So the idea is that it's an oceanographic research vessel, so go out to sea and it can research mostly on fish populations.
That's big. Yeah, air guns for a seismic, so that's the main problem, one of the big problems. You may or may not be aware, have you looked into or heard of the comfort classes that are available, that you would go to? These are regulations that set the thresholds. This is not for a marine device, so I don't really transfer that. Within the ship itself, the comfort classes 1, 2, and 3 that have criteria and standards set that you must meet these levels of qualified. D&D has the rules for that. And you set, the minimum vibration and noise levels in cabins and so on. They get tested and they get certified. Do you have any chance to look at any of that stuff?
Yes, I have looked at some of the classifications with IMO, and I am aware of some of those things, but I didn't have a chance to fully dive into those details.
Draft the back certification with all the stuff. Okay.
Yep.
Did you have time to look into things like agent closures and all that stuff? As many gensets, specific yachts, typically have agent closures for at least for the gensets. Is that something that you researched?
That is something that I have looked into. It definitely is possible to, in some cases, have an encasing going around the genset. The main issue with me was spatial awareness, and trying to make sure there was enough space for the exhaust coming out of it. That was the main reason why I never looked at it specifically for my vessel. Let's see. I would like to say a big thank you to the profs that that helped organize this event and get everything situated. And I'd like to also thank all the audience for taking your time to come here and looking at all these presentations. And a big thank you to all the people that presented and my class for making this a great experience. Thank you, guys.
Well, folks, that concludes our presentations and events for the two programs. I just want to echo what Anthony was saying. I thank everyone for all their efforts and what was put forth the last few days. The presentations were fantastic. The open house was a lot of buzz about that, and I deem it a success. I just want to say thanks to the students and parents. Couldn't do this without your support, and to the faculty and to industry who've been around helping out and giving their feedback for the students. It's been a good success. So a round of applause for everyone for the efforts. I just want to say thanks. I'd ask for actually both the classes, if you could meet me back in, we'll do it in the NARC classroom at around, I think some people want to do some pictures on that down here now. I'll give you another 20 minutes. So just after 12, I just have a chat with the classes there before we sort of send off and have things on. Again, thank you, everyone, and good luck.